Hi everyone. Let's take a first look at our Generation 4 silicon carbide FETs. My name is Anup Bhalla and I'm the VP of Engineering. UnitedSiC has a wide range of silicon carbide based FETs in the 650 volt to 1700 volt class, and our leadership position is cemented just not only by the breadth of the offering, but especially by these ultra low RDSA on devices, 7 milliohm at 650 volt and 9 milliohm at 1200 volt. And this portfolio is now being complemented by the highest performance technology on the market, our 750 volt Gen4 technology. And you can see the two new devices highlighted in this selector table. The first two devices in this Generation 4 750 volt platform, an 18 milliohm and a 60 milliohm, are offered in the industry standard 2 to 47 3-lead and the 4-lead package. So that is 4 products. They are AEC Q101 qualified. These devices retain the ability to be driven with a 0 to 12 volt gate drive because they featured an input FET with a 5 volt threshold, which has a plus minus 20 volt VGS max and is ESD protected. And so these devices can also use gate drives commonly used with silicon carbide MOSFETs, IGBTs, or superjunction FETs. They retain a 175C TJ max. Despite the very small die sizes of these silicon carbide JFET based cascodes, the R theta JC is kept quite low through the use of advanced wafer thinning and silver sintering technologies during packaging. What's most important is that this RDSA is delivered with very low device capacitance stemming from the small chip size, which makes the EOSS and COSS TR numbers very low. This is going to be shown to be useful for both hard and soft switching applications. The diode performance of the Gen 4 is even further improved over the Generation 3. The forward drop of the diode is very low and the QRR is very low and temperature independent. Gate charge for these devices is set by the silicon input FET. It's very low, and again, using this at high frequency puts less stress on the gate driver. The reason we selected 750 volt for the first launch of Generation 4 SiC FETs is because we wanted to enable the use of these devices in 500 volt bus applications. The devices are, of course, compatible with all 400 volt bus applications, and that's why we compare them in this document to available silicon carbide MOSFET competition and superjunction competition devices. In Generation 4, we have made a very large improvement in this figure of merit referred to as RDSA, which is the product of RDSA times area. Essentially, it means it's a measure of what resistance you can get from a device with 1 centimeter square active chip area. So the JFET that's used in making the SiC FET has a much better on resistance per unit area at 25C or 125C compared to any of the silicon carbide MOSFET devices on the market. And what this means is that in any given package type, we are able to produce 2 or 3 times lower on resistance. So this should continue our advantage in providing the lowest on resistance devices to the market as we fill out the portfolio. Since most of the applications of these devices involve switching at relatively high frequencies, it's not enough just to have low RDSA. You also have to optimize the switching losses. Because the chips have been shrunk so much, their capacitances have come down, and due to this decrease in capacitance, all of the switching figures of merit have improved. This chart shows the RDS EOSS figure of merit. EOSS is the minimum energy the device will dissipate during hard switching. So this would be, the limit of how well any given technology can perform in hard switching. And you can see this figure of merit is vastly better than the silicon carbide MOSFET devices at 650 volt, even though these are 750 volt devices. Soft switching is the preferred way to make DC to DC converters that are more compact with high power density. And the higher the frequency you use, the more compact they become. In order to enable that high frequency, you need a low output capacitance that can be charged up quickly, even at low currents. And this is why the RDS COSS TR figure of merit is important. And again here, the Generation 4 750 volt SiC FETs are far superior to the 650 volt silicon carbide MOSFET competition. And in a later chart, we'll see how they stack up against superjunction devices. But what's also more important if you're trying to run at high frequency is the 5 to 10 times lower gate drive loss that you can get with the Gen 4 SiC FET devices, which means the existing drivers will not run too hot. Finally, if there is more frequent body diode conduction during the dead time, the low drop of the body diode is very beneficial. The body diode drop of SiC FETs is much lower than that of silicon carbide MOSFETs. This was true both for Generation 3 and Generation 4, but driven by the shrink in the chip size and the reduction in the capacitance, the QRR of Generation 4 750 volt devices is significantly better than the Generation 3 devices that came before it. So this is beneficial in both hard and soft switched applications. This radar chart summarizes all the previous pictures in one slide. The figures of merit relating to RDS on A, which sets the conduction loss capability in a given package. The figures of merit for soft switching at high frequencies, RDS, COS, STR, the hard switching figures of merit, and then the superior body diode performance. In all areas, the 750 volt Gen 4 offers advantages over the 650 volt incumbent silicon carbide MOSFET devices. If we benchmark the 750 volt Gen 4 devices against the best-in-class superjunction standard and fast diode devices, a few things stand out. These devices, the Gen 4 devices, can be used in hard switching because the QRR is vastly superior. In fact, superjunction devices are seldom used in continuous mode hard switching, and therefore for totem pole PFCs, these Gen 4 devices are much superior. Not only that, if you look at the RDS COSS figures of merit, it is clear that they are so much better than superjunction devices that much higher frequency can be achieved using these Gen 4 devices. And the same can be said for the gate charge when running at high frequencies. The same gate drive circuits can be used because these devices are also compatible with 0 to 10 volt gate drive. They have a 5 volt threshold. So with these excellent low RDS-ons, the same sort of gate drive that you need for silicon superjunction devices, but with 1/10 the gate charge, you can see why the mid to high range of superjunction devices will benefit from a replacement using these SiC FETs, because not only are they cost competitive with those devices, they offer superior performance on every dimension. So now that we've looked at all the figures of merits that have been improved using Generation 4 technology, we can figure out what applications are going to benefit from these devices. So the devices are 750 volt. They have good hard and soft switching figures of merit. They can be driven 0 to 12 volt. The parts are now AEC Q101 qualified, which means the primary drivers for their application could be the automotive onboard chargers and DC-DC converters, where these devices will improve efficiency, cut losses, improve cost effectiveness and reliability. And they are ideally suited for the IT infrastructure space, whether it's in continuous current mode, totem pole PFC, or the LLC type DC-DC circuits. And the same advantages in hard and soft switching can be utilized in the solar inverter space and the energy storage space. So in summary, Gen 4 technology pushes the figures of merit achieved by silicon carbide transistors to new levels. We are the first company offering 750 volt devices. This should enable 500 volt bus applications. You can see that these are targeted towards all high growth areas, whether it's in EVs, energy storage, or the growth of IT infrastructure. A much wider portfolio of these devices is planned for 2021, from the very lowest RDS-ons to the highest frequency switches with higher RDS-on.